So, good morning. Welcome to Krishna's classroom. Last time we looked at the class of M star measurable sets script M and found that it is extremely rich in the sense that all the open sets belong to it, all the closed sets belong to it, the countable union of closed sets belong to it, countable intersection of open sets belong to it. So it's all extremely large, or we have a huge class of sets which may serve our purpose. So our attempt so far to construct a class of sets for which reasonably meaningfully the concept of length can be defined is successful. Now in this talk what we are going to look at is that the possible approximations to M star measurable sets by the so-called F sigma and G delta sets. That means using Borel sets which constitute what is called the smaller sigma algebra containing all open sets, or the containing the topology of the real line, is what we are looking at. So we can approximate the M star measurable sets from both inside and from outside. Okay, so let us work with that. Before that, we introduce the so-called excision property. Okay. Let A be an M star measurable set. That means A belongs to the script M. Be a finite M star measurable set. Contained B a subset of R. Then we have this result, namely M star of in what follows. This result is going to be a very handy tool. So I will use the Venn diagram again for clarity, because it's not easy to show general sets on R. So we have now B is there, A is a subset, the measurable subset with a finite measure. Now This can easily see. Since A is measurable, this is B minus A. A is measurable. I mean M star measurable. Is M star measurable? We have M star of B equal to M star of B intersection A plus M star of B intersection A complement. Now so this is equal to M star of A plus M star of this is because since A is a subset of and that implies M star of B slash A equal to M star of B see, remember we are assuming A is an M star measurable set, but we have not made any such assumption on E is any other. This is true. And that is what we are after. Okay, so this is called the excision problem. Now we give the approximation theorem. So let E be contained in R, then each of the following four assertions are equivalent to the measurability of M star measurability of. Okay, so let us write down the assumptions. These are what are called the remark later. The first statement is that for each epsilon positive, there exists an open set O containing E for which m star of is less than, that is one statement. Second statement is that there exists a G delta set G containing E such that m star of now these two statements are very interesting. What it says is that if E is m star measurable, then E can be approximated as closely as you want, in the sense that m star of O slash E is less than epsilon by open sets. And what you can prove in that case is that there exists a G delta set G containing E such that m star of G slash E equal to 0. I will make more remarks about it. Okay. So this is what you call the outer approximation. And the converse is also true. That means these two statements, not necessarily together, each one implies 2, and 1 and 2, 1 or 2 implies that E is m star measurable. Okay. Now we give the two more approximations. Now these are approximations from inside. Okay, so let me do. Third statement. Third statement, for every epsilon positive, there exists a closed set F let me write here. See, the fourth statement is equivalent to 3, as we shall see. There exists an F sequence set F such that M star of F E slash sequence. Now we look at the analogy of second with 4, first with third. So you have an outer approximation from using open sets and essentially with the G delta sets. So also you have an inner approximation with a closed set, closed sets, and with what is called a F sigma set. This is called okay. So let me use Venn diagram because on R it is difficult to draw pictures. Therefore, we do one thing. We prove the equivalence of the measurability of E with the statements 1 and 2. Okay. A similar procedure using De Morgan's law, one can prove the equivalence of the measurability of E with 3 and 4. We shall indicate the details. So let us start with the proof of the first statement. So assume M star E is M star measure. That's assumption. We are assuming E is M star measure. Now we show that 1 holds and consequently 2 holds, and then assuming 2, we can show that the measurability of, okay, so we will make a cyclic. So proof of 1. So this implies M star measurability statement. This is what we have. So case 1, the first case, M star of E finite. Okay. By the definition of the outer measure, M star of E, there exists a countable collection of open intervals that is, you are just using the definition. Intervals covers E and for which sigma, the length of IK, less than this comes from the definition that M star of E is the infimum of this sum for a collection of open sets IK such that E is contained in the union of that, and because of the infimum definition, it follows that there is a collection of open intervals IK whose union contains E and such that the total length of these intervals is less than M star of E plus epsilon for any epsilon positive. Okay, right. For any epsilon positive. Now, this is what is happening. So, this is again the Venn diagram. See, you have got, suppose this is the IK, or I will put it this way. This is put these are all IKs. So that E is inside the union of these IKs. I mean, I am talking about a countable collection, not a finite collection as I have drawn here. Okay. And the M star of E is the infimum of all this. Okay. So you have, what happens here? What happens here? So M star of E is the infimum of all this. And therefore, from the definition of infimum, it follows that you can choose a collection of open intervals IK whose total length comes arbitrarily close to M star E. And using that, you can get this inequality. So, this is the consequence of definition of. So, this is the consequence of that's it. Okay. Now what we do is define. So we have identified such a collection. Define O as the union of such IQs. That's the definition. Now O is open. Subset of R and by the definition of the outer measure, M star this is bounded by one to infinity length of ik, and this is of course less than M star of E. So what does it imply? It implies that M star of O minus M star of E is less than X. It's less than. Now since E is measurable, E is M star measurable and has finite outer measure. We have by excision property M star of O slash E is equal to M star of O and this is less than. That is exactly what we. So that shows the whenever M star of E is finite, the result holds. Now we take the case case B. Assume that is E is measurable and M star of E is infinite. Then E may be expressed as the disjoint the disjoint union of a countable collection of measurable sets Ek such that m star of finite for every k. So this is one of the results that we have. It's a countable collection of star measurable sets such that this is now we use case A. So what you have is m star of now use case A. Then what you get? Then what you have is this. For every open set, for every measurable there exists an open set OK containing EK such that m star of or what you do is for the number epsilon by you fix epsilon, take epsilon by 2 to the power k and then use the fact that m star of Ek is finite and Ek is measurable and therefore m star of OK there exists an open set OK such that this is true. What is it? Now let O define as union so each Ek is enclosed inside an open set and each of this will be naturally of finite. Okay. Then O is open because it is the union of open sets, right? And E is naturally contained in, because union of EK is contained in union of OK, right? And therefore O slash E is equal to union of E, which is contained in union K equal to 1 to OK slash. This is the crucial result. Okay, and that implies M star of is less than or equal to, this is countable subadditivity of M star and this is of course less than the way in which we have chosen OK. This is less than sigma okay, that is the condition 1. So we have proved that the measurability of E implies condition 1. Now we want to prove that what we prove next is one implies 2. Okay, I mean that's quite simple. For each natural, for every natural number K, choose an open set OK containing E and such that M star of less than. So what you are doing is now taking up E and enclosing it in a open set OK such that M star of OK slash E is less than Now what one does is the following. Define G to be equal to intersection of K. Okay. Now G may not be open. Okay, right? And G is a G delta set. G delta set, and we have E is contained because E is contained in each one of these. Okay, therefore this is right. Therefore, what we have since for each K slash E, G being the intersection of all K's, therefore G is in every OK. By the monotonicity of outer measure, we have m star of is less than or equal to m star of which is less than for every K. Okay, and therefore that is condition 2. So we have proved measurability of E implies 1 and 1 implies 2. So we have proved this. Now what we want to prove is that 2 implies measurability of E. So the next claim is measurable. Now the crucial result that we use is that any set of outer measure 0 is measured. This is a property that we have proved earlier. Okay. So, hence, a G delta set is an M star measure. And what we have is this. See, you have G, then you have E. So from this you have E is equal to G intersection complement. E slash E is this. So this is G slash E. G slash E. Okay. Therefore, you see G slash E is measurable, being a zero. Therefore, G slash E complement is measured. Which implies, see, M being an algebra, see what you have, G is M star measurable, G slash E complement is M star measurable, therefore their intersection is M star measurable. E is that is E belongs to E belongs to so that completes the proof E belonging to M implies 1 implies 2 implies that is equivalent to one and okay. What next? Now what we are asserting is that the an n star measurable set can be approximated from inside by a f sigma set. Okay. Now what you do is, and that is, so what is to be to that now this is the proof is similar, because you see, so note that we are now trying to approximate E from inside by closed sets and their countable now to demonstrate this is what you suppose you have a set E. What you do is we approximate this by something like a plus 1 by n or a plus epsilon, such that a plus epsilon e, the closed set a plus epsilon b. So what you are doing is you are going to write a, you are approximating with the union of the open sets, sorry, the closed sets a plus epsilon, or let me write epsilon n. So countable, take epsilon n, right? To have epsilon n tends to infinity. So we are getting an approximation of this set from, okay, right? You can prove this. I mean, this is just what happens. Now let us see how do we prove this. So we can use so you take, we approximate E complement, which is measurable, by open sets and G delta. Okay, so what you have? You have, this is what you have, E complement slash O You are approximating by an open set. Okay, what you have is this. Therefore, what you have O slash E complement. There exists an open set such that this is less than. Okay. Less than epsilon. Similarly, you have m star of G E complement is equal to 3. So what do you do? So this is using 1 and 2. We are now working on E complement. Now what one does is use this one. De Morgan's law. Okay. So you see that you take the complement of, so you can show that E slash O complement m star of this is less than epsilon, and m star of now you see that this becomes a F sigma and this becomes a closed set. Okay. So we can apply 1 and 2 and De Morgan's law. With the help of De Morgan's law, you can prove 3 and 4. So you can prove De Morgan's law and the excision. Okay. One can prove that immeasurable the artist just work on E complement, okay, and then apply this. Okay. So that completes the proof of this theorem. Okay. So I think I will stop here today, and then next time I will show that the m star measurable sets can be approximated. If it is a finite measure, it can be approximated by a finite collection of, as the union of finite collection of open. That will take up next time. Thank you very much.